Okay, in this lecture, I'm going to be talking about non-experimental designs and contrasting those with experimental designs. And specifically, we'll talk about what this means for trying to make causal attributions or saying that our independent variable caused changes in the dependent variable. And then I'll also go through and mention and discuss just a few examples of some non-experimental designs, specifically quasi-experimental designs. There's lots of different quasi-experimental designs, but I think if you know the basics of the ones that I'll go through, you can kind of figure out other ones as well. So just a quick review of causality, something that we talked about at length in experimental design. Remember, we have to meet 4 conditions to be able to say that our independent variable caused the changes in our dependent variable. First of all, you have to show that the conditions of the independent variable do differ on the dependent variable. In other words, that the IVs and the DVs are related. So we have to establish that the independent and the dependent variable co-vary, that the dependent variable does change in response to the independent variable. If there's no relationship between the two, we don't have cause and effect, and we don't have to worry about anything else. Also, remember, we need to manipulate our independent variable before we measure its effects on the dependent variable. That gives us that causal time sequence. In other words, the cause has to occur before the effect. This is one of the problems we run into in correlational research, where you're measuring your independent and dependent variable. When that happens, you oftentimes can't establish the causal time sequence. And then we need to make sure that the participants in the different conditions of the independent variable, our groups, are roughly equivalent, so that they don't have certain characteristics that differ between the groups. The easiest way to do that, remember, is just through random assignment. And that rules out confounds. In other words, if we compare existing groups that we didn't randomly assign, those groups might differ in lots of other ways. And therefore, when we get our results, we don't know, was the results due to the independent variable, or was it because these groups already differed in important ways? In other words, we have potential confounds. And then finally, we have to control other extraneous variables during the course of our study, making sure that our participants are treated and experience everything the same except for the independent variable. And that's ruling out confounds as well. So the takeaway point here is that you get this stuff, these 4 conditions, through the design of your study. And specifically, experimental designs meet these conditions. Non-experimental designs typically can't meet 1 or 2 of these conditions. And so it's the design that helps determine whether you can say cause and effect. Statistics, you can use lots of statistics, lots of different statistics to analyze the results of an experiment. It doesn't really matter how you analyze the data, as long as you're not violating assumptions of your statistical analysis. And you're going to have cause and effect because of the design. So it's not the statistic that tells you cause and effect, it's the design of the study. All right, just a quick review. We've kind of already touched on some non-experimental designs before. We've talked about research that gives us descriptive or frequency evidence. That kind of research is often non-experimental in nature. Descriptive research can be things like case studies, it could be naturalistic observation. Frequency research could be surveys or questionnaires or doing polls of people, trying to find out about the frequency of something in a population. Typically, we're not testing hypotheses here. We're not looking at cause and effect. That's not even a goal of that research. Relational, correlational, associative designs are all the same thing. We can at least show that variables are related. But remember, just because we have a correlation doesn't imply causation. We talked about the third variable problem and the directionality problem. That's a problem with going just from correlational research and trying to make causal claims. And one of the reasons, this is a big difference here between correlational research and experimental. In experimental research, we're manipulating that independent variable. In correlational research, we're measuring the independent variable. And so we can't say cause and effect because you're not manipulating that independent variable. And just a quick review, remember, of the directionality problem and the third variable problem. So if we measure people's levels of stress, so let's say we're doing a longitudinal study and we measure people's level of stress and we measure whether or not they get cancer over time, okay? And you're going to find an association there probably, that positive correlation, higher stress, higher risk for cancer. The problem is that because that's purely correlational, we have a directionality problem. Is it the stress that's causing higher rates of cancer, or is it getting cancer causes higher rates of stress? So one problem with trying to make causal claims from that correlational research. The other problem is we could have an unknown factor, a third variable, that's causing both. For instance, it could be that if you eat like a really high fat or high red meat diet, that might be associated with higher levels of stress. And it might also be associated with higher levels of cancer. So a third variable could explain why stress and cancer are related, okay? To eliminate these kinds of problems, then, that's why we run an experimental design. It rules out confounds or third variables, and we also, because we're manipulating the independent variable, we've established that causal time sequence. Now, another design that I haven't talked about in lecture yet is quasi-experimental designs. These typically are kind of in between correlational designs and experimental designs, in that really good quasi-experimental designs are better than purely correlational designs at getting us closer to cause and effect. We still can't say cause and effect because we're not running a real experiment, but they often are better at ruling out confounds than some purely correlational studies, okay? But we still can't technically say cause and effect in a quasi-experimental design. And so you might wonder, well, if we want the strongest evidence, why don't we always just run an experimental design? Why would we ever run these quasi-experimental designs? And there's several reasons for this. One, ethically, sometimes we can't or we shouldn't do an experimental design. If I'm looking at car crash and death rates in car crashes, and I want to know, does a seatbelt law make a difference? So a state that has a seatbelt law versus a state that doesn't have a seatbelt law. I might compare states. Now, those states might differ in other important ways. So I'm not going to be able to say cause and effect there because I have confounds that might explain why the states differ in their death rate other than seatbelt use. But I can't ethically, if I wanted to run an experiment and really get at cause and effect, I would have to randomly assign people, when they're driving around, to either wear their seatbelt or not. Okay, and then, drive around for 10 years, and then we'll see who dies and who doesn't. You can't do that, obviously. That's not ethical. In addition, some things that we want to study are completely outside of our control, so we can't manipulate the independent variable. If I wanted to know, are there higher PTSD rates in communities that have suffered a tornado? Okay, so these kinds of natural disasters, they typically increase PTSD rates. I can't manipulate, I can't determine which people are going to be exposed to a tornado or not. Once again, I'd probably be left with comparing existing groups. If a tornado hits a small town, If I can find a somewhat similar small town, maybe about the same size, but that didn't suffer from a tornado, and then go in and kind of measure PTSD rates in the two communities, that might give me some ideas about whether a tornado might influence PTSD rate. I can't say causally it does, because those two communities probably differ in other ways other than just being exposed to a tornado. But I can't manipulate some variables. And then sometimes I'm just interested in subject variables anyway. I want to know things like gender. Are there gender differences in helping behavior? Well, I can't randomly assign, I can't manipulate gender, even if I wanted to. But for some questions, we're not really interested in causal evidence. We just want to know, is there a difference between these groups? And if we're just interested in a difference between the groups and we don't want to make any causal claims, quasi-experimental designs, like the natural groups design, are fine. Okay, I also want to come back and just mention something about independent variable. I alluded to this just a few minutes ago. Unfortunately, well, the way that we've talked about independent variables so far is that in an experimental design, this is the causal variable, it's the one that the researcher manipulates. Unfortunately, researchers who also use non-experimental designs will also sometimes refer to an independent variable, even though it's not the same thing as an independent variable in an experimental design. Independent variables in these non-experimental designs, they're called many things. They all mean roughly the same thing. They're sometimes referred to as a measured independent variable, sometimes as a subject variable, like gender, or a quasi-independent variable. All of these terms mean the same thing. It means in non-experimental designs, we're not manipulating that variable, we're measuring it. Okay, and once again, this goes back to the discussion that we had in the previous lecture, and also I mentioned at the beginning of this one, that if you have a measured independent variable, you can't say that that causes changes in your dependent variable, because you're not meeting that one condition of manipulating the independent variable before you measure the dependent variable. Because of that, there's potential confounds with your results. So researchers who use like a subject variable or a measured independent variable, in the back of their mind, they may be thinking that they think that IV caused the changes in the DV, but they can't claim that. And you certainly wouldn't write that down when you're writing up a research report, because that's a claim that you can't support because you're not running a true experiment. And then dependent variables, those are the same in experimental and non-experimental designs. Dependent variables are always measured. Once again, this whole idea of measured IV versus manipulated independent variable, you can't say cause with the measured independent variable. It's kind of like, if you're visiting your grandmother's and you think about swearing, something bad happens, you stub your toe or whatever, and you want to swear, you think about swearing, but you probably don't because grandma won't look very kindly on that. It's the same thing here. Researchers probably would like to say that a measured independent variable causes changes in their dependent variable, but they don't. It's just not socially acceptable. All right, so go through a quick example kind of showing you some of the problems with the different designs and why we don't say cause. Let's say we want to know, does caffeine hurt exam performance? Okay, and I know a lot of people think, well, caffeine, probably helps improve cognitive performance and thinking and, gives you this boost of energy and focus and those sorts of things. And there's some claims with that. But there's also some evidence that caffeine, because it has this arousing function, that arousal could be misinterpreted. If you're sitting down and you're taking a difficult exam and you notice that your heart's racing, you notice that, maybe you're starting to sweat a little bit, you might interpret that not as arousal due to the caffeine, but as arousal due to test anxiety. And then that might actually hurt performance. So let's say we're interested in this. Can caffeine actually hurt performance on tests? Well, if we were doing descriptive research, okay, like a naturalistic observation, we could go in and observe people taking an exam and, you know, does it look like the people that are drinking coffee while they're taking their exam, does it look like they're struggling more? We could kind of describe that. That's really horrible at getting at cause and effect. Same thing with frequency. If we were looking at frequency, we could ask people, we could do a poll and ask people, do you think that caffeine hurts exam performance, yes or no? And we could describe then, you know, the percentage of people that think caffeine hurts exam performance, but that's very different than whether or not caffeine actually does hurt exam performance. So descriptive research in answering this question is going to be virtually worthless. Correlational research, now what we could do is we could measure maybe the level of caffeine in a person's system. I don't know if you can get like caffeine level out of a blood draw or not, but we could try to figure out some way of measuring how much caffeine a person has taken in. And then we can also get their exam performance, and we can see if there was a relationship. You know, is there a negative correlation here? The more caffeine a person has in their system, the lower their exam performance. Okay. That could tell us whether the variables are related, but it can't tell us cause and effect. Okay, remember, we can't say cause and effect because both of these could be influenced by some third variable. It could be that the amount of sleep that you got the night before, that determines how much caffeine you need in the morning, and it also determines or influences how well you do on the exam. If you didn't sleep very much, you probably have a harder time concentrating. Quasi-experimental design, we could just ask people. We could divide them into two existing groups. Did you drink any caffeine this morning before the exam, yes or no? If yes, you're in this group. If no, you're in this group. And then we compare those two groups' exam performance. But we still have this kind of third variable or confound problem. It could be that people that did drink caffeine and didn't drink caffeine differ in other important ways. And one of those ways might be influencing how well they do on the exam. So quasi-experimental, in this example, it's kind of the same as a correlational. We still have third variable problems. Obviously, the best way to do this is randomly assign people to either get a placebo drink with no caffeine or an energy drink that has a certain amount of caffeine in it. And if, as long as you hold all other factors constant, they taste the same, you know, they smell the same container, whatever, and you treat the participants during the test exactly the same, if you then find that the caffeine group did worse than the non-caffeine group, you'd be able to say that caffeine caused worse performance. Okay? You'd be able to make that causal claim. And so, takeaway point here, once again, the first three designs, descriptive, correlational, quasi-experimental, we still technically can't say cause and effect. Only in experimental designs can we say that. All right, so let's go through a couple of examples of quasi-experimental designs. Most of these quasi-experimental designs are some version of the one group pre-test, post-test. Other quasi-experimental designs typically do different things to this basic design. They add on more observations or another comparison group or something like that. So if you understand this, you can kind of figure out the other quasi-experimental designs. So here, let's talk a little bit about the notation. So the notation here, the O's stand for observation. That's basically measures of the dependent variable. And so this is actually a pretest measure of the dependent variable. The X means we introduce the independent variable. In quasi-experimental design, they sometimes use the term treatment. So if you see treatment, basically means the same thing as like a quasi-independent variable. And then we're measuring, we have a post-test measure of the dependent variable. So we have a pre-test measure of the dependent variable. We then introduce our treatment or quasi-independent variable, and then we measure the dependent variable again, a post-test. Okay, and it's one group total, so that's why it's called the one group pre-test, post-test. So let's go through an example of this. Let's say I grade the first exam in research methods, and the class does horribly. Such a low score. You know, it might have been the lowest exam score on average I've ever had. So super low. So I think, crap, I need to do something different so that performance on the next exam is better. And so I go to, let's say, a couple of teaching sessions at Elbogen Center for Teaching and Learning on campus, and go to a lecture, and they talk about the importance of group work and hands-on problem solving and those sorts of things. So I decide I'm going to kind of change the way I'm teaching the class. So if the class was heavily lecture-based, now I'm changing it so it's a lot more group-based, where students are working together to solve problems. So much more hands-on. Okay, so here, if we go back up to the design here, the first observation, this would be the first exam score. Exam scores are going to be my dependent variable. What I want to know is, did my change in teaching, switching to more group work, did that change in teaching result in higher exam scores? So my pre-test measure is the first exam score. I then introduce the treatment, which is introducing group work into my teaching, and then I look at the exam scores on the second exam. Okay, and let's say I find a huge shift, that first exam was super low, second exam, on average, the class is much higher. Can I then conclude that, oh yeah, my change in teaching, that caused the exam scores to go up? Hopefully you can see lots of problems with this. The one group pre-test, post-test is almost worthless in terms of trying to make causal claims, because there are so many problems with it. You can think of tons and tons of reasons why, other than a change in teaching, might result in higher exam scores on the second exam than the first exam. Okay? Think about some of the things that happen here. It could be that the first exam scores were super low because of a history effect. It could be that before the first exam, maybe there was like a really important basketball game that went into triple overtime, and it didn't finish until 1 o'clock in the morning. And most of the students in the class went to the game, and they got home really late, and they didn't really have much of a chance to study, or they were super tired. And therefore, early in the morning when they're taking that research methods exam, it's hard to concentrate and they don't do very well. And then before the second exam, nothing special happens. There was nothing keeping them up late at night. Everybody got a good night's sleep. Everyone had a chance to study, and therefore everybody did much better. In addition, students individually, if they bomb a first exam, they're probably doing things differently, studying harder, studying more, so that they can improve their grade on the second exam. So it may not have anything to do with the teaching change. It might be that students just changed how they were studying from exam 1 to exam 2. We also might have the statistical effect of regression to the mean, where when you start with super low or super high scores on a pretest, there's usually more movement towards the mean on the second test. So if everybody just bombed the exam, they couldn't hardly score any worse. Well, that means there's very little variability or very little room to do even worse on the second exam. But there's a ton of room to do even better. And because there's more room for variability above their low score, that's why you tend to see scores go up a little bit on a second exam, is it could just be regression to the mean. And there's lots of other possible explanations. One thing that happens typically between exam one and exam two, a bunch of students will drop or withdraw from a class. Well, most likely the students that drop or withdraw from a class are students who are struggling. So what you've done is you've removed some people that scored really low on the first exam. They didn't take the second exam. If you remove those low scores, that will also artificially elevate the scores on the second exam. So there's lots of other explanations for why a change could occur. And that's why the one group pre-test, post-test isn't terribly useful. But you can make modifications to this that make it a lot better. One modification is something called the interrupted time series design. Basically what you're doing here is you're increasing the number of pre-test measures of the dependent variable and the number of post-test measures of the dependent variable. And it doesn't have to be exactly 4, but you typically want the number of observations before the introduction of the treatment to be the same as the number of observations post-treatment. In this example, I have 4. 4 measures of the dependent variable, then we introduce treatment, and then we measure 4 times the dependent variable again. So let me give you an example of this. Let's say you have a good friend and they run a flower shop. And they know that you've taken statistics classes and research methods classes, so they know that you're a good person to ask. They've recently paid an advertiser to run a series of commercials for them to see if they can increase their business. And say, let's say you just ran a one group pre-test, post-test. And so this is 1 month, and this would be the sales for that month. And then this is the sales for the following month. And in a one group pre-test, post-test, so sales is your dependent variable. In between those 2 months, we're going to introduce our treatment, which is the advertising campaign. So we have 1 month, we look at the sales there, we introduce the advertising campaign, and then at the end of the month, we look at the sales there. And we see that there's this huge increase in flower sales. So the question is, okay, great. Have I shown that the advertising campaign works? No, because it's a one group pre-test, post-test design. You're not ruling out lots and lots of alternative explanations. The most obvious one is, what time of year are we talking about here? If this is January, so this is your flower sales in January, and this is your flower sales in February, well, Valentine's Day is in February. So it could just be kind of like a history effect, that because it's February and that's when Valentine's Day is, sales are always going to go up in February. So it might have had nothing to do with the advertising campaign. It could have just been a history effect. Okay? But if you run an interrupted time series design, you can kind of eliminate that as a possible explanation for your results. Let's say this is our results from our interrupted time series. So here's the 4 months prior to introducing the advertising campaign, and sales are kind of low or flat. We then introduce the advertising campaign, and now for the next 4 months, the sales are much higher. Okay, this pattern here, I mean, it's not completely flat, but that will never happen. Ideally, we'd just like to see it. This is flat, and then there's a jump, and then it's flat again, but it's much higher. But that's never going to happen in reality. There's always some play in the data. But if you see this pattern, you can be fairly certain that it's not just because of the effect of Valentine's Day. Because if it was just Valentine's Day, then sales should have went back down for the next 3 months. and that didn't happen. They stayed high. That's stronger evidence that it might be due to the advertising campaign, and it's not just some history effect. Okay, and so with the interrupted time series design, by adding more measures of the dependent variable, it helps you rule out some confounds, because now we would have to find some confound that explains why sales went up and stayed up for 4 months at the very same time that the ad campaign was running. Okay. Now, to make this design even better, you could add what's called with reversal. So interrupted time series design with reversal. And this is what the notation looks like. So here we have multiple measures of our dependent variable, or observations. These are pre-test measures of the dependent variable. We introduce the independent variable, or our treatment. Then we have multiple post-test measures of the dependent variable when we're still being affected by the treatment here. Then, this is the part that's being added, we then remove the independent variable again. So we take away the quasi-independent variable or the treatment, and then we measure the dependent variable 4 more times. Okay, so here what we're seeing is the effect without the independent variable, the effect with the independent variable, and then the effect again without it. And so ideally what we want to see, if our advertising campaign for the flower sales are working, is this. We want to see that in the 4 months before the ad campaign goes in, that sales are low, but as soon as we introduce our ad campaign or the treatment, sales go up for 4 months. And then when we remove the treatment or our advertising campaign, sales go back down. You might expect some lingering effect here of the independent variable, because people still kind of remember your commercials or your ad campaign, but you'd probably expect sales to kind of go back down the further away you get, or the longer it's been since you've run that ad campaign. Okay, so low sales, high sales when the advertising campaign is there, and then low sales again. Be fairly convincing evidence that it might be due to your ad campaign. You still technically can't say it is, but in order for a confound to be, in order for your results to be due to a confound, it would have to explain this specific pattern. Why was it low for 4 months, then high for 4 months, then low? Okay, and you've ruled out a lot of potential confounds because of that. And just to give you another example of something you could look at with these two designs, let's say you're interested in the death penalty. One claim, which as far as I know, I don't think there's actually any evidence for this. One claim about the death penalty is that if you institute the death penalty, violent crime will go down, because potential murderers will rationally think, I can't kill someone because then you'll kill me. The problem is most crime is not committed. Most crime, it is not due to rational thought. It's due to kind of emotions or irrational thought. And that's why it doesn't really affect violent crime rates. But let's say we're interested in this. One thing we could do is, let's say we have a state that didn't have the death penalty, and now the legislature passes the death penalty. What we could do, our dependent variable is the number of violent crimes committed, and it'll be, let's say our observations are each year. So 1, 2, 3, 4 years. 4 years before the death penalty was instituted, we look at what the violent crime rate was those 4 years. And then we look at the 4 years after the death penalty was implemented. Ideally, what we would want to see is that violent crime was kind of up here, death penalty went into effect, and then violent crime was lower for 4 years. Okay? Provide some evidence that maybe the death penalty makes a difference. Even better, and this is going to be problematic because you'd have to have a state that actually did this, have a state that instituted the death penalty and then they later get rid of it. That would be ideal. So then you could look at for multiple years, what was the death penalty or what was the violent crime rate before the death penalty? What was the violent crime rate while the death penalty was in play? And then what happens to the violent crime rate once you remove the death penalty? Does it go back up again? Okay, that would provide some evidence. Once again, you're getting close to causality, but technically you can't say that. One other kind of modification here to the basic pre-test, post-test test is the non-equivalent control groups design. And so now, rather than following one group over time, which is what we're doing in the interrupted time series designs, we're going to be comparing existing groups. And because these groups are already existing and we couldn't randomly assign people to those groups, that's why it's called non-equivalent. It's because these groups exist already and therefore they might differ in other ways. So let's say we're going to do a pre-test, post-test, non-equivalent control group design. So you can see that each group has a pre-test. One of the groups is going to get the treatment, and then both groups have a post-test. So we're measuring them on our dependent variable before one of the groups gets a treatment, one group gets a treatment, and then you measure post-test for both. Ideally, what you want to see here is that they are the same at pre-test on your dependent variable, but then they differ at post-test. That would provide some evidence that maybe it was your treatment that led to the changes. The difficulty with this design, though, is if you show that they already differ at pre-test, that makes it difficult to interpret any results you get after that because you've already shown that the groups differ in some important way on the dependent variable. So now when they differ at post-test, you don't really know what that is. Is it because of these pre-existing differences, or is it due to the quasi-independent variable or the treatment? So a good example of this is the DARE program. Some schools implement DARE, some schools don't. And so we can't run an experiment on this because we don't have control over which children go through DARE and which children don't. We can't randomly assign them. So the best we could probably do is compare two schools, the children from two schools. One school uses DARE, the other school doesn't. So the first thing we're going to do is we're going to measure, our dependent variable in this example will be self-reported drug use. So we measure self-reported drug use at pre-test. Hopefully, the two schools have similar rates, because if they don't, then anything that happens after that is going to be hard to interpret. But let's assume they do. They have similar rates of drug use that they're reporting. Then one of those schools gets the DARE program, and then a year or two later, we measure drug use again. So the best pattern here, which would indicate that DARE is working, would be that the two groups are similar here, but the DARE group at post-test has lower reported drug use than the control group. Okay, that's what we want to see. And I'm pretty sure research on DARE suggests that there's no evidence that it actually reduces drug use, but people like the program and that's why it sticks around. Okay, but that's the pre-test, post-test, non-equivalent control group design. That's what it looks like. Okay, I think that's all I have for this lecture. Once again, most versions of quasi-experimental design are some adjustment to the basic pre-test, post-test design. All right, so today I talked a little bit about some of the important differences between experimental designs and non-experimental designs. We've previously talked a little bit about descriptive or frequency designs and correlational designs, so I focused primarily on quasi-experimental designs in this lecture. Okay.